Factors affecting the rate of dissolution. So dissolution means like dissolving a solute into a solvent to create a solution. And there's different things we can do to make substances like dissolve quicker. So we're going to talk about that first. So first you can increase the surface area of your solute. So that means like if your solute was in a tablet form, that's what you see in the picture here with the seltzers. Like if it was in a tablet form, then you just have, if it's a circle, you have your three sides, like the top, the bottom, and then the rim, right? The outside. But if I break it in half, now I have the top, bottom, the outside, plus that interior is now exposed to whatever liquid I put it into. If I broke it into quarters, I have more exposure. The most exposure would be grinding it up. So if you had a solid that was in like a crystal form and you grind it into a powder, that will help the amount that can dissolve and like the rate at which it dissolves. It'll go faster. Agitation is another one. That's stirring. Also, that could be adding heat. Basically, you're making the molecules move faster. So if you are stirring it, you're promoting like faster movement from within. If you're shaking it, that's promoting faster like movement. Heat is giving them more energy so that they move faster. So doing that will help the dissolution process as well, making it go faster. So solubility is being able to dissolve into a specific solution. We use the term like dissolves like. Typically, polar things will dissolve in other polar things. Nonpolar will dissolve in nonpolar. So that's like a basis. And then at certain temperatures, you can have solubility more than at other temperatures. So we're going to take a look at all of that. So solution equilibrium. We know equilibrium is finding the rate of the forward reaction equaling the rate of the opposite reaction, but it's true for phase changes too. Basically, those two rates, they find an equilibrium where they sort of equal each other, and sort of both things are existing. So we can call that like the dissolution rate or the crystallization rate. Dissolution is going from like the solid into the like aqueous form. Crystallization is pulling out the solid from the solution. A saturated solution means you have exactly the correct amount of solute for the given amount of solvent. It means that if you added one more molecule of the solute, it wouldn't dissolve. You have exactly the right amount. So this is given specific masses of the solvent, and the solvent has to be at a specific temperature. But when we have that, we get a point on the graph that is actually saturated. We're going to look at that graph in a little bit. Super saturated means you have too much solute in there. If you add more, it's not going to dissolve. It's going to stay in its crystal form, at which point you need to do one of the things that we said before, like heating it. Heating it will raise how much you can put in. But supersaturated means nothing more will dissolve. Unsaturated means there's not enough solute. You can put more in, it will continue dissolving. So we will look at that in a graph form, but I do think these pictures are kind of helpful. So if this is the exact right amount in this middle picture where it says saturated, if that is the exact right amount of solute and solvent like ratio, then I can see here, obviously I have significantly less dots, which means I can add more of my solute. And then here I have crystals that formed at the bottom because I have too much of my solute in the given amount of solution at this specific temperature. Okay, so like I said, like dissolves like, which means that polar will dissolve other polar molecules, and vice versa, like nonpolar will dissolve nonpolar. But here's an example of water or sodium chloride, which we know is an ionic compound. Sodium is a metal, chlorine is a nonmetal, so it's ionic. That means in its crystalline structure, ions exist. We have positive sodium ions and negative chlorine ions. And when we add that salt to water, we know it dissolves. I mean, we see that every day with like oceans. We don't see little salt particles. You can't put your hand in the water and feel salt, but we know it's in there. And that's because this is what's happening, where we have a crystal structure put in water, and then the water comes with its positive and negative parts and pulls apart those positive and negative chlorines and sodiums. So water, because it's polar, it can dissolve anything else that's polar. So those are mostly ionic compounds. Maybe some covalent compounds that are highly polar. Water could dissolve those as well. The term immiscible means that the solute will not dissolve. So that's an example would be putting there's an example down below, the lithium fluoride into toluene. Toluene is a nonpolar solvent. Vice versa, you could put something that is nonpolar into a polar solvent. So you could put something like oil and water, right? They're not going to dissolve into each other. They're going to separate because one is polar and one is nonpolar. Miscible is the term we use when it will dissolve, specifically with nonpolar substances. So something like methane, which is a nonpolar solute, you could dissolve in benzene, which is a nonpolar solvent. So I just said methane. Methane we can force into liquids. Any gas we could force into liquids. We need a certain pressure and we need a certain temperature, but we can do it. Gases are typically already moving faster. We know that from kinetic molecular theory. If they're in their gas phase, they have as much energy as possible, right? Solid has the least amount of energy, liquid has the medium amount of energy, and gas has the most energy. Those molecules contain the most energy. So if I want to make a gas dissolve into a liquid, I have to lower the temperature, I have to slow those gas molecules down, and I have to increase the pressure. I have to physically push them into the liquid. So soda is a perfect example. When you open a soda bottle or a can, you hear that tss sound. That sound is the release of the pressure because it is pressurized inside that can in order to keep those carbon dioxide gas bubbles in the liquid. So soda is an example of where there is a gas dissolves in a liquid at higher temperatures, that gas gets released. That's why when you let a soda sit out on the counter for long periods of time, you go back to drink it later and it's no longer carbonated. It's because those gas molecules heated up enough that they were allowed to escape the liquid. So soda will only stay bubbly at low temperatures and high pressures. So we can see that here on this graph. All of these lines indicate, an infinite number of points at which you are saturated. You have exactly the right amount of solute in the given solvent at a specific temperature. So here, this brown line that goes across, you can see it's sodium chloride, NaCl, that's table salt. And you can see that as I increase the temperature, I don't have a very steep curve. I mean, it does increase how much I can dissolve. So at 0 degrees Celsius, I can dissolve about 38 grams of sodium chloride, and that's in 100 grams of water. That's the definition of that y-axis there, axis. So, but as I go up to 100 degrees Celsius, now I'm at 40. So it's a 2, 3, 4 gram difference from 0 to 100 degrees. But if I look at something like potassium nitrate, that is this light blue curve here. At 0 degrees, I can only dissolve about 14 grams of sodium nitrate in 100 grams of water. But at 60 degrees, I can dissolve, I would say 108. And that's the most I can dissolve. That is the saturation point. Now, I might give you a point on the graph. I might say something like, at 40 degrees Celsius, you put in 90 grams, so 90 grams, 40 degrees Celsius of potassium nitrate. Tell me, are you supersaturated, saturated, or unsaturated? So I'm above the line, right? If I go down on my 40 degrees Celsius, I'm above this blue line. Therefore, I'm a supersaturated solution. The blue line is the exact right amount. That is completely saturated. And then below the line is unsaturated. So if I'm here at 50, well, let's pick something that's on the line. There's nothing really on the line. That's pretty close, but we'll stick here. So if I'm at 40 degrees Celsius and I put in 50 grams of sodium nitrate, this light blue line, if I put in 50 grams and I say, okay, how many more grams can I add until I'm saturated? You can see that it's saturated at 40 degrees Celsius at about 62, 63. So you would say 12 to 13 grams would be your answer there, or your best guess. But if I said something like you put in 90 grams at 40 degrees Celsius, how much did not dissolve? You would say that's 10, that's 20, that's like 26. I would say like 26 grams. You might also be asked, if I have, 90 grams of sodium nitrate, at what temperature would I be able to dissolve all of that mass in 100 grams of water? So you would come over here and you could read the temperature. You could say, okay, well, right there, that's about 52 degrees, 53 degrees. So reading that graph will help you sort of understand saturated, supersaturated, and unsaturated. This line going down here, we have the sulfur dioxide. A lot of that's what like the curve looks like for gases, where as we get warmer, less solute will be dissolved. So again, at colder temperatures and traditionally higher pressures is where we're going to get gases to dissolve.